it will be a Moodle based quiz. Hope you can see the PPT. So last time, we were talking about either static or slowly moving flows. And we discussed three things: principal stresses, Moore's circle, and the yield loci. So to just go over this, so what we said is that if you have any system, and let's say you are given with respect to this coordinate system xy, and then you are given another surface whose normal makes an angle alpha to the x-axis. So whenever we talk about a stress, obviously we have to say what surface is the stress acting on, because it's stress per unit area, force per unit area. So supposing it's acting on this surface, and that surface is characterized by the normal vector n. So then this normal stress that is acting on this surface, red surface over here, is given by this, where alpha is this angle. So sigma xx, sigma yy, sigma xy are given to us, and if you want to calculate what is the normal stress on this surface, it's given by this formula. And the shear stress on the surface is given by this formula. And then we saw that if we take the derivative with respect to alpha, we can find out the angle at which the normal stress is maximum. And then if we rewrite this same equation, if we rewrite it in terms of alpha p, which is defined as just alpha minus alpha m, then the stress is just given by this, normal stress is given by this, shear stress is given by this. So what it says is that obviously when alpha is equal to 0, then you have, this is sigma m plus tau max. Sigma n is the mean value of the stress, tau max is the difference divided by 2. So if you add those two up, you see that it is just sigma is equal to sigma max. So when alpha p is equal to 0, sigma is equal to sigma max. That's expected because alpha p is the angle from the principal axis. Now, if you see this, these are basically the parametric equations of a circle. Or if you just write it in this form, sigma minus sigma m whole squared plus tau whole squared. So you'll see there is tau max squared cos squared of 2 alpha p. This is tau max squared plus sine squared of 2 alpha p. You add it up, you will just get the equation of a circle. And that circle center is at sigma m and the radius is tau max. And this is called Moore's circle. So at any angle alpha p, so when alpha p is 0, you add the maximum value of the normal stress, sigma max. And then as that angle increases, and of course over here the shear stress is 0. And then as alpha increases, your normal stress decreases and shear stress increases until over here you have the maximum shear stress and a mean value of the normal stress. And then as you keep on increasing, your shear stress decreases until it reaches 0 and you get the minimum value of the normal stress. And then you go further and it will go in exactly the opposite direction. So this tells you the entire range of normal stress and shear stress that you will get acting on any surface. And then, so as I said last time, everything over up to this point, this is material independent. Whether you take water, you take granular material, you take a block of steel, anything, this is always going to be true. That if you are given these stress components XX, YY, XY, then you can calculate the Mohr circle and it will tell you what is the stress at any angle. So that is always the case. Now what is new and what is particular for granular materials is this thing called the yield criterion. So this is essentially the stress that's required to actually make the material yield or fail. And what it says is the shear stress for the material to yield is a constant times the normal stress. So if you put it on the same graph, essentially the yield criterion will give you a straight line. So it's like this is for plus and this is for minus. So and at the point of yielding, what you will have is the Mohr circle will be tangent to the yield criterion. Okay, and if you see this from the geometry, then you will get this. And this is something that you can extend the yield criterion. Sometimes you will have cohesion, in which case your yield criterion will become what was there earlier plus cohesion, which can also be written as, you can take f prime common or tan beta common. F prime is equal to tan beta, and so this will be sigma by sigma a. So tan beta times sigma a will give you C. So this is essentially a cohesive force. We have learned about cohesion. You can get cohesion due to liquid bridges or surface forces and so forth. And so here, if you just look at this, you see that your shear yield stress is 0, not at sigma equal to 0, but at sigma equal to minus of sigma a. So you have a sort of tensile force that is acting, but otherwise it's the same. And at the point of yield, using the same sort of geometrical argument, the radius is still tau max, and then the hypotenuse, which is given by here, is equal to sigma m plus sigma a. So that's why this is there. So it's just a small change from this. So for a cohesive material, you will get this additional tensile stress which you have to overcome. So this is really what characterizes granular materials. And what I want to do next is, say a little bit more about this eigenvalue approach and then stress balance equations. And then how do we solve these stress balance equations? What is the closure? And then a couple of examples. So I won't do everything today, but at least some part of this. This is what I'll do in this particular topic. Okay, any questions? So this is what we have been doing. So we did up to here. So we could either write it as, we could show this in terms of tau and sigma, or we can write the yield criterion also in terms of the principal normal stresses. Here sigma 2 and sigma 1, they could be either sigma max or sigma min. This line is when sigma 1 is sigma max, and this line corresponds to the case when sigma 2 is sigma max. And the yield criterion becomes the ratio of these two is equal to K. So let's try and let's go ahead with this. So we have now reached lecture number 14. We are 1/3 through the course, I guess, or maybe more, little more than halfway through the course. Okay. So what do we want to talk about today? So, we would like to, I think that one thing that I could possibly redo is this part on the yield criterion. So I said it on there, but let me just do this again. It's okay. So this is supposing with cohesion. We saw this in there. And what we have in this case, it's a little bit of a repetition, but anyway, it doesn't matter. Let's just look at this one more time. So really the only thing that we have to see is that the yield criterion starts from a negative number. And so this is our sigma m, as we always have. This is 0. This is sigma a. Shear stress, normal stress. So at the point, this radius is tau max. The radius of the circle is tau max. And you can see that this distance is sigma m. So the yield condition, as I wrote down, is tau y is equal to f prime into the normal stress plus the cohesive force which we can also write as, instead of f prime, we can write it as tan of beta into sigma plus sigma a. Of course, we know that tan of beta is equal to f prime, and beta is called the angle of internal friction. And then from here we also see that sigma a can be just simply written as equal to f prime c, which is also equal to tan beta into c. And c is usually referred to as the, am I writing it the wrong way? I'm just writing everything wrong. So we have, actually what is there is c is equal to sigma a times f prime, which is equal to sigma a times tan of beta. I wrote it the other way around. And c is for the cohesion. This is what makes the particles stick together. And in this case, we have sine of beta, as we just saw. This angle over here is beta. So sine of beta, which is opposite side, that is tau max, divided by the hypotenuse, which is sigma a plus sigma m. So this is the criterion. But now we can easily write it in terms of, we know that sigma m is just the mean value, which is sigma max plus sigma min, is the mean value of the principal stresses. And then tau max is just sigma max minus sigma min divided by 2. If we substitute for all these things and then simplify, then we'll get that sigma max by sigma min is equal to what we had got before, which is 1 plus sine beta divided by 1 minus sine beta plus you get one more term which is 2 sigma a into sine beta divided by 1 minus sine beta. So you essentially get a similar thing as before. So you will get an additional term here. So this term is due to cohesion. And you can see that if cohesion is 0, that is if sigma a is 0, then you get back our old expression which we had derived here. You can see this is what we had derived earlier. And now you will get this plus this. And in the previous lecture we had seen that we call this ratio as capital K. Okay, so that's one thing new. But then there is another thing is that we can write the principal stresses as simply eigenvalues of the stress tensor. So we know that really what we are doing when we do all this more circle business, when we did all this stuff, the main thing that we want to do is we start with, if you remember, we started with this matrix for the stress, and by doing all these derivative with respect to alpha and all, then in the new coordinate system we transform this into a purely diagonal tensor or a purely diagonal matrix. So essentially, what we are trying to do is we are trying to get it in this form, and these you can say are nothing but the eigenvalues of this matrix. So essentially what we are trying to do is, what we say is that we want to find the normal vector n so that when we do sigma dot n, now remember we have already had a long discussion of this. So sigma dot n is nothing but the force per unit area that is acting in the direction n. So when we do it like this, when we do sigma dot n, you will get a vector. And what we want to say is that this vector should be in the direction n. So that there will be no tangential component at all. Okay, so just to say it slowly again. So if this is our coordinate system, x and y, and again I will draw this thing here. This is our, or maybe we draw it a different color so it looks brighter and we feel less sleepy. So let's say this is my surface, nice red color surface, and this has a normal vector n, and that makes an angle alpha. But we are not bothered right now about alpha, so I'm going to just remove this. So I don't want it. So this is what I have. I want to find out what is this. So I want to find out the normal vector. So now what will happen is sigma dot n in general will give you another vector, right? So sigma dot n is a vector, and that is the force acting on the on this surface which has a unit normal n hat. Now we want to choose, now if we define this as t, the tangent vector, then t dot sigma dot n, this is the force, of course, this is of course per area. Acting, this is, I'm repeating everything. I know it might be boring, but this. So this is the force that's acting, but it's in the direction t. And this we call as a shear stress. Now what do we want? Our principal axes are such that when n is along the principal axis, the shear stress is 0. So this is what we have already found out. The shear stress is 0. Okay, now someone has to tell me. Now if this is 0, then what does this mean? That means that the component of this vector in the direction t is 0. So what? How should I draw this? So instead of drawing it like this, instead of drawing this vector over here like this, how should I draw this vector? So basically this vector has no component in the direction t. So what should I draw this vector as?
Along the normal direction.
Exactly. So basically this vector should be along the normal direction. So again, different color. So I will draw this here. So this is if you have n is along the principal axis, then sigma dot n must be along n. So what is it, if I have to write that in a mathematical form? So that means sigma dot n must be in direction n. And what does that mean in mathematical form? This means that sigma dot n can be simply written as a scalar times n, right? So this is basically an eigenvalue problem. So finally, you know where eigenvalues can be used. Must have learnt about this in math, but you can see now here is an example where you need to know eigenvalues. And if you want to find out these eigenvalues, what is the way of finding the eigenvalues? So to find them out, we simply solve determinant of sigma minus lambda I is equal to 0. So this is the reason why we can write it as a eigenvalue problem. And I want to say that earlier whatever we have done is, the earlier derivation was for a 2D system. So it was just a 2 by 2 matrix. but this is valid for 3D. That is, you're taking X, Y, Z components all. So it's a generalization of what we had done earlier. And so now if we do a simple example, what are the principal stresses of sigma given by, again I'll just write down a simple one, 4 root 3 and 2. So one method is the old one what we used, in which case sigma max and sigma min by through the alpha method they were simply given as sigma xx plus sigma yy by 2 plus minus sigma xx minus sigma yy whole squared plus 4 tau raised to the power of half divided by 2. So this is method 1, and if I substitute for this is 4 plus 2, 6 divided by 2, so this is equal to, so I'll do sigma max and sigma min. So minus sign is for sigma min and plus sign is for sigma max. So 4 plus 2 is 6 divided by 2 is 3 plus minus, and here what we have is 4 minus 2 whole squared is 4, and then 3 root 3 squared is 3 into 4 is 12 raised to the power of half divided by 2, which is equal to 3 plus or minus 16, square root of that is 4 divided by 2, so 3 plus minus 2, which is equal to 5 and 1. So those are the sigma max is 5 and sigma min is 1. So this is if you use the old method. Now we have learnt a new method, and what is the new method? It's to find the eigenvalues. Eigenvalues are the principal stresses. So the method 2 is just determinant of sigma minus lambda I is equal to 0, which in a usual way we can write down as 4 minus lambda root 3 and 2 minus lambda. So that is this matrix. Determinant of that is those two lines is equal to, now you will remember this is just 4 minus lambda into 2 minus lambda minus 3 is equal to 0. So we open this out, you will get lambda squared minus 6 lambda plus 8 minus 3 is plus 5 is equal to 0. And this, if you do the quadratic formula, you will see that the roots of this equation are simply 5 and 1. So essentially what you will see that the eigenvalues are the same as what we had calculated before as expected. So, one of the things I mentioned here is this is valid for 3D. So what is yield in 3 dimensions? What will it look like? So one way is to extend more Coulomb to 3 dimensions. And So what do? Do you do a sphere? No. So you can essentially, what we can say is that we consider two directions at a time. Okay. So again we write same thing, sigma and tau, but just consider two at a time. Because in 3D, in 2D, you are getting sigma max and sigma min, but in 3D, you will get three principal stresses. You'll get sigma 1, which is, let's say, larger than sigma 2, which is larger than sigma 3. So sigma 1 would be sigma max, sigma 2. Let's say if we are considering two of them, sigma 1 and sigma 2, I can plot them here. Let's call this is sigma 1, and let's call this as sigma 3, and let's call this as sigma 2. So if we consider sigma 1 and sigma 2, so this will be sigma max, this will be sigma min, and I can draw a circle that goes through this, right? Like how we had done here, right? So this is sigma max, sigma min. Where have I done it? Here, sigma max and sigma min, and the center is sigma mean. So here, when I'm dealing with just sigma 1 and sigma 2, then I have a center over here, which is sigma 1 plus sigma 2 divided by 2. So when I consider the two largest roots, I will get this circle. Then let's consider the medium and the smallest. So for that, this will be sigma max, this will be sigma min, and I will get another circle which is here, and this one is given by sigma 2 plus sigma 3 divided by 2. So this is the mean value, and of course this sigma 2 and sigma. So when I consider, I get one circle for each pair of them. But when I consider sigma 1 and sigma 3, so then this is sigma max and this is sigma min, and then you can clearly see that the circle is going all the way around, and this has a center over here. Little bit complicated with sigma 1 and sigma 3. So you know what it says is that essentially the yield, because these other circles with sigma 1 and sigma 2 and with sigma 2 and sigma 3, they lie within the big circle. So circles for sigma 1 comma sigma 2 as the principal stresses, and sigma 2 and sigma 3 as the principal stresses, lie within the sigma 1 and sigma 3 circle. So that is clear to you, right? So effectively what happens is that when yield occurs, let's say this is a yield criterion, the yield will always be determined by the smallest and the largest and the smallest. That is sigma 1 and sigma 3. Is this okay? Do you agree with what I'm saying? So, you know, what you can imagine is I've got a 3D system and I've got sigma, the whole stress tensor given by sigma xx, sigma xy, sigma xz, Then again sigma xy, sigma yy, sigma yz, then sigma xz, sigma yz, and sigma zz. So this is my matrix. I'm given all these values. You can see this is a symmetric matrix, so there are 6 independent values. From this, if I solve the eigenvalue problem, which is sigma dot lambda, sigma dot n is equal to lambda n. So now I've got a surface. I've defined some surfaces on which the stress is purely a normal stress, and you get a diagonal matrix. Then I will get 3 eigenvalues for this: sigma 1, sigma 2, and sigma 3. So those are 3 eigenvalues, and for each pair of those eigenvalues, I can get a circle. Sigma 1 and 2, which is the two largest, then sigma 2 and 3, which is the smallest and the middle one, and then sigma 1 and 3 gives you the circle. But this circle is the biggest, and these other circles lie within that big circle. So the yield criterion will always apply only to the biggest circle. And so this is what you can imagine that the yield in 3 dimensions. Okay? Is that okay? Can you understand that?
Yes, yes, yes.
So now we have done one new topic today, or 2 new topics we did today. One is when you have cohesion, what happens? And you can see that there is a change in the yield criterion. Then the second new topic we did was that there is now a new method we can use to get the principal stresses, that is by solving an eigenvalue problem. And this method is nice because you can go up to 3D, and when it is 3D, you can easily apply the Mohr-Coulomb criterion by considering the largest and the smallest principal stresses, because that gives the largest circle. Okay. This is so much nicer than a paper and pencil, no? Because I can easily do all these things. Difficult to do this when you're writing in. Okay, so now we go for the. So what is our whole objective? We want to actually try and solve and try and get what is our stress in the system. That is really our goal. And we have found out that we have done only one thing, that is we have seen that how the stress changes as the surface orientation changes, and then based on those arguments we have been able to write down a yield criterion. But if we want to solve for the stress distribution, or more precisely the equilibrium in the system, then we have to write down the governing equations for the stress, and for doing that type of derivation we can consider a material volume within the system which has a unit normal S, and let's say this has a surface, bounding surface given by S. So if we look at this, then we can write down that the total force exerted by the stress acting on the surface, so sigma dot n is the force per unit area acting on the surface, and then ds is the area. So this is the total force acting on a surface element ds, and then if we integrate over the whole surface, then this is just equal to the body force on the system, which is the gravity force. Excuse me. So the total force acting on the surface. This is the total force due to gravity. And these must be balanced at equilibrium. Now, if I apply the divergence theorem, which we briefly looked at, onto the left-hand side, of this equation, the divergence theorem converts a surface integral into a volume integral. So then we get a volume integral, and this sigma dot n just becomes divergence of sigma dot over the volume. Now, since this volume that we have taken is arbitrary, whatever is this equation must be valid at every point. So this essentially gives us a point-wise equation which says that divergence of sigma must be equal to rho b of g. Okay, since the volume is arbitrary. So I can always, if this is not satisfied at some point, I can always pick a small volume around that point, and then this equation will be violated. So the only way that this is true for every volume V is that if this equation is true at every point in the system. So you essentially get the stress balance equation, which says that the divergence of the stress tensor is just rho b times g. Rho b is of course the bulk density of the material. Bulk density means total mass per volume. So that is mass of the particles plus the voids divided by the volume. And the same thing if we put in component form, then divergence of sigma, we have learned how to do this. You know that we can use this, that the divergence, the nabla operator is just Ex del by del x plus Ey del by del y. So in 2D, in 3D it will be plus Ez, and then we know the tensor form for sigma. If we simplify everything out, then this divergence will give us a vector equation, so we can write it in component form as sigma xx. Where gx is the component of the gravity in the x direction, and similarly sigma in the y direction, the balance is. So I did this simple derivation without going into too many details, but this is a standard equation you will find in all textbooks. for the stresses. So if you look at even Navier-Stokes equation or Cauchy equation and put velocity equal to 0, you will get this. This is the stress equation. So these equations essentially say they just say that the sum of all forces acting on a system are equal to 0 at equilibrium. There is no acceleration, so the sum of forces is equal to 0, and this is what this equation says. And the gravity force is balanced by the stress in the system. So you can see from here, how many unknowns do we have in this? So if we assume that the bulk density is a constant, so bulk density is given to us. So then how many unknowns do we have?
3.
3 unknowns, correct. Sigma xx, sigma xy, and sigma yy. So we have 3 unknowns. And these are sigma xx, sigma yy, sigma xy. So these are the 3 unknowns. How many equations do we have?
2.
So obviously we can't solve this problem. So we need something more. And so that essentially tells us, because again this equation is valid for any system. Like I've been saying, this could be valid for water, for a block of steel, for particulates, for anything. It doesn't say what the material property is. So we need to incorporate, to solve this equation, we have to say something about material behavior. So we have to put in something about the material, and only then we can solve it. Now for a liquid, we know one thing. And that is that in a liquid at equilibrium, just if you remember your fluid mechanics, we know that if the liquid is static, then there will be no shear stress. So immediately one of the components drops out. So essentially for a liquid, this component is 0. So then there will be 2 unknowns and 2 equations, we can solve it. Because we know that in a liquid, it cannot sustain a shear stress. However, in a solid, that is not true. You can have, even in a static system, you can have non-zero shear stress and normal stresses. So we do need one more equation. And the condition that we use to solve that is called the condition of incipient failure. So, what it sort of says is that the material behaves as if it is about to yield. That means basically what you can say is that your tau is equal to f prime sigma at all points. So this is what is the condition of. So this will give us one additional equation. So what this essentially says that sigma max divided by sigma min is equal to k. And we already know, that sigma max and sigma min, they are all functions of sigma xx, sigma yy, sigma xy. Right? So if we are given these components, we know how to calculate sigma max. If we are given these components, we can calculate sigma min. And this gives us a relationship between sigma max and sigma min, that is k. So obviously that gives us one additional equation to calculate sigma xx, sigma yy, and sigma xy. So this is really the material behavior that we will use, that at the point of, at every point in the fluid or in the solid, you are at the point of failure, so that the principal normal stresses are always related by this constant k. And so we can write the governing equation, and we'll see later how to do it. But we can always get one more equation in addition to these two. So this will be the third equation. This is the third equation that we will have. So we have three equations and three unknowns to solve for it. Okay. So with this, I'm going to end the class, and in the next class we'll do some examples in which we will use these three equations, this, this, and this, to actually solve and try and get some stress distribution when you have just static materials. Materials are just sitting there. Okay. So I'll end with this. Please have a look at the programs that I have uploaded. I think I have now put in the right format, so you can easily download them. And if you like, we can even have a session where we can help to get you to run those programs by yourselves. And if you're facing difficulties, we can sort those out. So over this weekend, please try and run those things. But very importantly, try and familiarize yourself with the LAMP scripts, because homeworks and project will be based on that. So thank you and bye-bye.
Thank you, sir.
Thank you, sir.